Okay, so we've been thinking about the principles, where we are, where we want to get to, the importance of soil organic carbon. We're now moving on to think about the practice. Okay, if we can agree this is important, if we can agree that we all want to have more carbon in our soils because it does us good in terms of the production system, and also potentially we may be able to make money out of it, we need to know how much we've got, where it is, and what I can do to increase it, or whether I should even be increasing it on different parts of the farm or the estate. And that's actually really difficult. Lots of people will come and say to you, oh yes, I can come and baseline your carbon. I can come and tell you how much carbon you've got in your farm. It's actually really difficult. And what I want to demonstrate in the next half a dozen slides is why it's difficult, the approach we've taken within the Rothamsted Carbon Quester partnership that we've been working on, because it has to be robust. The number we come up with for our farm in terms of how much stuff is there, it has to be robust to the point that some kind of verification company or verification body can come and look at your methodology and say, okay, we can have confidence in that number. So it's not going to be a number, it's going to be a number with some confidence intervals around it, some uncertainty around it. We're never going to be able to say, 100% that's how much carbon you've got. And it's also got to be scalable. So issues of scale are really difficult and important in this area. Do I want to know just how much carbon is in this bit of my field, in the whole field, in my whole estate, or on the whole cluster? And that's relevant to the scale at which we're proposing we're going to manage carbon, or we're going to invest in this natural capital. Are we going to do it on a field scale, an estate scale, or a landscape scale? And they are the issues we've been grappling with over the past 6 or 12 months. And I'm going to illustrate the approach that we've taken. I know some of you have been involved with this in terms of allowing Tim and his team to come onto the farm. And he said, well, we want to go to this many fields. We want to go to these fields. And what I'm going to describe here is the rationale and the reasoning behind that. So this kind of brings us to today and to the cluster. And these are the farm outlines, the estate outlines of the cluster. And again, what we want to do is say how much carbon is in there. How much carbon have we got as a baseline? And then we can interpret that baseline in terms of the headroom that Stephan has been talking about. So this is how much carbon you've got. This is your current land use. This is how much clay you've got in that soil. So this is where you could get to. This is where you are. This is where you could get to. This afternoon, we'll be talking a bit more about how you can get to there. But for now, we're talking about baselining. How do we decide? How do we quantify our starting point? How much stuff we've got? Hopefully I'm not teaching Granny to suck eggs here in terms of introducing some of the issues and challenges to do with it. But obviously the sampling intensity is really important and needs to be adjusted by area. So we can't just say, okay, we're going to go and measure every 100 meter, every hectare, we're going to do one sample point. Because there's a trade-off between how intensively you take your measurements and the certainty that you can have for your number, depending on the scale. So if you're just interested in the amount of carbon in this field, yes, I could take a dozen samples on a grid and that will give you a very precise estimate for that field. But obviously we can't do that on every field on the estate and every field in the cluster. So there's a trade-off between the intensity of sampling and the certainty we can have about the number that we can come up with. And also, part of that uncertainty will be how good our method is for actually measuring the carbon at each of those crosses. So if we're doing it from space, or we're doing it from a drone, the uncertainty to do with the number of carbon that you come up with at each cross will be much bigger. We will say it will be between 1% and 2.5%. Much bigger than if we take a physical soil sample and send it to the lab, and they'll come back with much tighter confidence intervals. So if you are going to use a rough estimate of carbon, you're going to use a drone or a satellite or whatever, you need to have many more measurements to account for that lack of precision. And you'll look a bit later at the new methodology that we're using, the spectral analysis, the handheld sensor. Obviously, the uncertainty and the precision of that is different from the lab samples. So the work that we've been doing with yourselves and with your samples is trying to find the optimum sampling intensity. How many do we need to do? If you've got, I don't know, a 500,000 hectare farm, what's the optimum number of samples that you need to take if you're using this methodology or that methodology that trades off the precision with the cost? And that's the product, if you like, that we want to come up with. But there's some quite difficult thinking that needs to go on behind that. So once you've come up with the sampling intensity, you know, I've got a 500 hectare farm. I've decided I'm going to use this methodology, which is a combination of lab samples and pointing my machine at the soil. This is how many samples I need to take. Where are we going to take them? And secondly, it's not good enough just to use a grid. It's not good enough just to say, well, I'm going to do it here, 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 because you also need to take into account the variation in your farm. We've thought a lot already this morning about how much carbon you've got will depend on your historical land use, and it will depend on your soil type, how much clay you've got in your soil. So not all fields are equal. And also I've mentioned there that it will depend on some finer management differences and also topography. And you need to take account of all of those differences on the farm. So if you were on a completely, what we would say, homogeneous farm, everything was the same. It's all winter wheat, oilseed rape, barley, whatever. It's all the same soil type. Yes, you could just do a grid. But if you've got different bits on different bits of the farm, then you have to make sure that your sampling captures and reflects that variation if you want an accurate baseline number. And that is called a stratified sampling scheme. That's where we weight the samples according to the different land uses. And that's where the land app has been incredibly helpful for us. I'm just illustrating this from the first farm, that Shruton Parker farm that we worked on last year. So what the land app are able to give us are those data layers. So when we're deciding where are we going to come and measure the carbon on your farm so that we can scale up and give you a number for your carbon stock for your estate, we need to know this variability. So we need to know the variability in the soils, which you can see in the different colored blobs, the different soil series. And we need to know the variability in land use. So we need to overlay the land parcels. In this case, we just looked at arable at winter cropping. So these are all winter crop fields. So there's no differences in land use, but you can think, well, some of these fields might be different colors if they're in pasture or arable or different systems. So you need to assign your samples according to that. And then if you look on the table on the right, sorry if this is getting a bit too detailed, that's where you've got different ways of measuring the carbon. So the analytical chemistry is kind of your gold standard. And if you look down the table there, they're your different soil types. And we've allocated the samples according to how much you've got the different soil types. You can see that we need the fewest number of samples there to get a number for that estate using wet chemistry, because it's very precise. We can have a lot of confidence in the number. As soon as we start using the spectrometer, the handheld spectrometer, you see the sample number goes up. And that's because we've got slightly less confidence in the number it's giving us. It's one step removed from measuring the carbon directly. And you can see that the number of samples you need goes up. And it depends on whether you just point the sensor at your fresh soil, or you dry it, or do some kind of processing. So these are the thinking and the sums that we've done for this project to try and come up with the optimum number of samples, such that the number we give you for your estate, you can have confidence in, and it will have some intervals of uncertainty. And down the line, you know, you can go and you can say with confidence to somebody who's buying that carbon that, yes, we're sure this is how much we've got, and we've got that scientific integrity behind it. So back to where we are now. This is again downloaded from the land app, showing you the variation in the soil series in the cluster. So this is what we've got to cope with. And obviously you can look at this at different levels. We can say, well, let's design a sampling scheme for the whole cluster, or let's do it estate by estate, which is what we've done with Tim and what we've been doing over the past 6 months. And then, so we have the soil series, and we also have the different land uses. And so what we need to do, and what we have been doing, is you overlay those things. And that needs to be done for every new estate that we go to. So we need to know that spatial variation before we design the sample scheme. But hopefully, from what I've said, you'll have got the idea that the numbers we're coming up with are really robust. They're robust and they're scalable. And all this demonstrates is the orange bar are the sampling that we've done, and the blue bar is the total area, or the proportion in the total area. And that just illustrates that our sampling is representative of the variation on the ground. But again, it's a very robust protocol that we've come up with that can be then applied to any estate. Okay, are there any questions about that?
Sorry about that. It's me again. So this is about how actually we actually did the practical work on the ground. So just it shouldn't take too long. So, I mean, John already explained a little bit how the sample sites were selected, but then in the field, so this is the sample sites like what field was actually sampled. But when you're in the landscape, we try to make sure that we are not too close to the edge of the field where you have often edge effects. We try to avoid like fence lines or when you have this where the animals drink, or the gates where the animals walking. So this was just general considerations when we did the sample on the ground. So what we did is, I mean, we are thinking about this. There's these two approaches, right? You either make a point measurement, or you do the W measurement, which is supposed to be an average for the whole field. Maybe again about the standardization, but what we used as the basis for what we thought was the best to do was basically a FAO guideline, right? And so, first of all, each point is georeferenced, so you can come back in 5 or 10 years and find the same point again. Then we said this is a geospatial sampling design, so it's representative for a 100 square meter area, and then the different lengths of the arms are actually supposed to give a good average for these 100 square meter. That's the baseline for this. We had this cross made out of cord, so that we always got the same points. So when you come back in 10 years, you actually will sample the same points again. And then we sampled in 2 depths. Again, most of the organic carbon is in the topsoil layer. We sampled basically 0 to 10 and 10 to 30, which should usually cover about 70 to 80% of the carbon in the soil. And we sampled basically from these 5 points. So you have 5 subsamples. You put them in a bucket. That's 1 sample. 5 samples for the lower depth. Yes, I mean, meanwhile, it seems to be more realistic also to think about, you could also use the double use strategy, right? Because more and more of the sampling companies, they can georeference each individual point of the W, which you would need to do, right? If you deviate quite a lot of that, yeah, you can also, basically you can push the result in the direction you want, right? You can sample more at the bottom slope or more at the top slope, and you will get then, depending a bit, a change in organic carbon. Bulk density is still the big problem. How to measure, sorry?
Like I say, I've been thinking about that a lot, but because we've been splitting the fields according to different soil types on the ground data,
yeah,
putting a W across the split field, you need to do 2 Ws.
Yes.
And so then where do you start your double way to finish it? So it goes back to the point of actually gathering that sediment particle size data is actually quite important, so that you are, that sample is sampling that 100 meters square type of sediment in that type of land use. Sorry.
Yeah.
It's been playing in my mind as well. Why not doing, why not?
It's just before I didn't even think about it possible, because I think I had to, the location of each individual point, and a W is usually 15 to 20 points. So it gets a bit tedious.
Well, like you said, you're standardizing.
So of course, in the sampling itself, there are basically two bottlenecks. One is the analysis, right, which you send it to the lab, takes time, all this. The other one is actually the bulk density. And we didn't really solve that problem yet, right? So we still sampled with rings. So you have a metal ring of a defined volume, you hammer it into the soil, you take it out, you weigh the dry sample then, and that gives you your bulk density. And in our case, for the two layers, basically, we placed our ring in the center of that layer, and therefore hope to get the average bulk density for that layer. I mean, John again shows a little bit of data with soil moisture, and it indicates that it actually did work quite well with bulk density measurements. Yes, this is about these definitions, what is what. So soil carbon is the sum out of the organic carbon and the inorganic carbon. So you have to analyze both independently. Soil organic matter basically stands for this standard formula C6H12O6. So it's the whole, including the oxides and the hydrogen. So to get from soil organic matter to soil organic carbon, you would basically divide by the standard number is there 1.75. Actually, in most cases, it's done the other way around. So you measure soil organic carbon, then you multiply by 1.75, and then you say, this is my soil organic matter, right? So just to have these cleared. Yeah, just remote sensing. I spoke to quite a few specialists, and I don't think it's possible yet, right? What you can make is estimates, as John already explained. So you can make an estimate based on the land use. We saw much more carbon in pastures than in arable land. You can get data from the soil map, again, the Cranfield data. They have a few samples. And so you would use this data and average it, and then make your map from remote sensing. But it only can give you the trend. Yeah. And I mean, for pastures or so, you don't even see the soil. So you couldn't use any spectral readings from satellites or so to improve your estimate. It can only provide at the current, at least, can only provide a rough estimate of the soil organic carbon. It will never be good enough. Well, don't say never, but it will not good enough the next 10 or 20 years to really see the small difference we are looking for from 1% to 1.2%. I don't know that. So, and usually you also always need ground tracing, right? If you establish a system which uses satellites, you will have to go down and take samples. Yes, we do think wet chemistry so far is the gold standard. And there are different methods again in wet chemistry. So what we say is the best method is this Dumas method, which is the LECO is the standard equipment used for that, where you heat up the sample and all the carbon is vaporized. You measure that amount. So that gives you total carbon. And then you use a Primax where you add a little bit of acid to only break down the inorganic carbon, and then you deduct one from the other. Of course, most current measurements, if you send a sample into a lab, they will usually use LOI, loss on ignition. So basically the sample there is heated up to 400 degrees to measure only organic carbon. Problem is, depending on the amount of clay, you have basically very water between the clay layers, which is then also evaporated. So that's part of the error of the measurement. And the other error is that you also evaporate part of the inorganic carbon. So when you look in the literature, the error is goes up to 20–30%. So we just don't think loss on ignition is adequate for this. And this is the same for the FAO report. The recommendation is not to use LOI. I did recently, so part of why we're a bit behind here is because actually our instruments broke down for some time. So I checked with the commercial lab, NRM, if they could do the analysis for us. So meanwhile, they do offer, for example, the LECO and Primix method. But one problem is still that you have to weigh each sample to know the amount of carbon per gram of sample. Now, the weighing is actually it takes time in the lab. So if you have to weigh 1,000 samples in, you do it to 3 decimals of grams, so it's down to the microgram. It takes time. So what they do is they scoop. So they use a volume measurement and say, okay, each scoop weighs so much. Now that is again a bit an assumption, which again adds to the error of the measurement. So these are a bit the catches. So then we come to the spectral methods. So spectral method is you send some light on your sample and then you measure the reflection or the absorption. And these kind of methods are increasingly used in soil science. Since about 20 years, they are working on that. And I just have 2 equipments. No, I don't. You don't see the second equipment. Sorry about that. So this, the number 1 here is again, this is our gold standard for spectral instruments. So, but this is quite big, so you can't really move it. It stands in the lab. You have to prepare your samples, and then it provides very good estimates for soil organic carbon for texture, for example. Problem is that it's still cheaper, much cheaper and easier to do than the wet chemistry, but still it's time consuming. So we were looking into this handheld tool, but that's really relatively new. So it's came out about 2 years, I think. The first one was released. There are not many of these which are really handheld. There is an intermediate standard, but it's still handheld, but it's a backpack, and you have to do the measurements. It's quite, it's not that easy. So we really think that this handheld can work. As John said, it will be less precise than the wet chemistry or even the big machine here, Tensor. But we do think it can give good estimates, and just needs more measurement then. You always need the calibration. So you cannot use spectral measurements. So I make a model to estimate soil organic carbon for these soils here. And then I go 200 kilometers further north and want to use the same model. You shouldn't do that. So you can only use the calibration for soils which are similar to one you calibrated it with. That's where you can measure it. So we always need this ground truthing in a certain area. I mean, ideally, we would get a model which works for the whole of England and Wales. We're working on that, but we don't have it yet. That's when you come in, Cathy. I think you have to say some words there yourself.
Okay, so yeah, just to describe the using a portable spectrometer instead of, as Stephan was saying, using wet chemistry techniques in the lab, which involve a lot of soil processing. So you have to dry the soil, mill the soil, weigh the soil. So in theory, instead, you could use a portable spectrometer either in situ, so directly on soil in the field, or you could take it to the barn and just dry the soil, which should give slightly better results because it removes the moisture. And if you've got big moisture bands, that can interfere with your signal to noise detection. Or you can kind of crush the soil up a bit and then you get a really good contact with the spectrometer. So that would be like your final process stage, which should give the ideal results. So yeah, I'm going to talk about, as John mentioned, the sampling we did last year in Essex at Marsh Farm. because your results, I'm afraid, we've not managed to get through that yet because we only just got the wet chem back the other day. So I'll talk about these results. And yeah, so we've got two spectrometers. As Stephan said, we've got like the kind of the super one, which is portable, but it's much more expensive. And then we've got a really small handheld, which I'll show you later. And they're both, the first one is wavelengths in visible and the near infrared region, and the very portable one is just light in the near infrared region. And yeah, as Stephan said, you basically you correlate your spectral information from the soil. So you'll have lots and lots of peaks, and you do, so it's basically a multivariate analysis because you've got so many peaks. You correlate that to your single measurement of organic carbon as it's been measured in the lab. So then when you make a future measurement of your soil, just based on your spectra, that will link directly to your calibrated prediction of soil organic carbon. So a quantitative measure of your soil organic carbon. So we basically, you use an algorithm called Kennard-Stone, which selects your calibration set, which is the red dots here, and a separate validation set, so a completely different set of soils from those that are in the calibration to test or to validate how good your predictions are. So both sets, the calibration set and the validation set, have known soil organic carbon values, and you see how good your prediction with the spectrometer was at predicting those. So this is some near spectra. It's got the gradient of organic carbon there. So you can see basically the lighter coloured lines have more organic carbon. They've basically got lower absorbance, so they're probably reflecting more light. And yeah, so this is the results from the Marsh Farm last year. So I've got the better spectrometer, or the bigger, more expensive spectrometer on the top there, and then the small spectrometer, the handheld, is just the one at the bottom, and we didn't have that in time to do the fresh analysis, unfortunately. But with the big spectrometer, we analysed the data as fresh, so in situ, in the soil, in the field, just dried, so just left to dry, like at air temperature, and finally dried and sieved. So as I said before, you kind of expect, going through the 3 processing stages, you kind of expect a better prediction, and that's what we found, just simply because you're removing interference and you get a good contact with the scanner. So with the fresh soils, you're still getting an R-square of basically 0.7. So the closeness to the one-to-one line is, yeah, like 70%. Whereas your error, your RMSE, which basically how far you off in terms of the accuracy of the measurement, so how close you are to the actual organic carbon measurement, it's varying at around 0.4%, so nearly 0.5% of carbon is the error with your fresh samples. With the dried samples, it actually wasn't quite so good, and that's sometimes because they're big hard clumps and you can't get a good contact with the scanner. So it actually wasn't as good as the fresh samples. And then with the fully processed soils that you've dried, you've bashed down, you've got a nice homogeneous mixture, and you get a really good contact with the scanner, you get the best R-square, which is 0.9, so nearly perfect on the one-to-one line. And the RMSE, so your actual accuracy of the prediction, is varying at around 0.3%. So it's still not perfect, but it's quite good. And the same again with, as I say, with the small handheld. This is just on the really processed samples. The R-square wasn't quite as high as with the expensive equipment, but the RMSE was about the same, about 0.3%. And
sorry, can you explain what RMSE?
yeah, it's basically just how far away, on average, how far away your predictions were from the actual measured value in the lab. So if the measured value was 1.5% carbon, say, if you've got an RMSE of 0.3%, you could be anywhere, your predicted value could be anywhere from 1.3% to 1.8%. So you've got a 0.3% error around. Yeah, so depending on how accurate you need to be, that may or may not be, you know, a big issue. And these are some very preliminary results from your soils. So I haven't got very far. And this is just with the larger spectrometer. And these are the fresh soils. So nothing done to them, just dug up out of the field and scanned directly with the spectrometer. And we're getting in the validation set, which is the one on the right. So the validation soils are completely separate to those that were in the calibration set. R-square of nearly 0.8%, and actually the RMSE is quite high there. So again, it's nearly 9%. So that's nearly a whole percent around your carbon value, but that's because of these few outliers there at the top. I haven't been able to figure out what those ones are all about yet, but after going through the data a bit, like I say, this is really preliminary. We only got the carbon results the day before yesterday, so I think that's it. Yeah.